Welcome back to our channel. Today, we're diving into the fascinating world of quantum physics and debunking some of the biggest misconceptions surrounding this mind-bending field. From entanglement to the double-slit experiment and superposition, there are plenty of myths and misunderstandings that we'll be unraveling in this video. Understanding quantum physics is crucial in today's world as it forms the basis of many modern technologies, from computers to medical imaging. By dispelling common myths, we can gain a clearer insight into the true nature of quantum phenomena and appreciate the incredible advancements made possible by this branch of science. Get ready to be amazed by the mysterious and counterintuitive aspects of quantum mechanics. We'll be exploring how particles can be in two places at once, how they can influence each other instantaneously regardless of distance, and how observing them can alter their behavior. So, sit back, relax, and let's journey into the quantum realm together. Misconception 1: Quantum entanglement is instantaneous communication. One of the most common misconceptions about quantum entanglement is that it allows for instantaneous communication between particles, regardless of the distance separating them. In reality, quantum entanglement is a phenomenon where two or more particles become correlated in such a way that the state of one particle is directly related to the state of another, no matter how far apart they are. Quantum entanglement is like a magical bond between particles, where their properties become linked, even if they are far apart. Imagine two entangled particles as dance partners who always move in sync, no matter the distance separating them. While this connection seems instantaneous, it cannot be used for direct communication. It's as if the particles share a secret language that only they can understand, making quantum entanglement a mysterious and captivating aspect of physics. Quantum entanglement is a fundamental aspect of quantum mechanics and plays a crucial role in various quantum technologies, such as quantum computing and cryptography. An example that illustrates entanglement without communication is the Einstein-Podolsky-Rosen (EPR) paradox, where two entangled particles exhibit correlated properties even when separated by vast distances. Sabine Hossenfelder, a renowned physicist, emphasizes that quantum entanglement does not allow for instantaneous communication or the transfer of information faster than the speed of light. Instead, entanglement showcases the interconnected nature of quantum particles and the limitations imposed by the laws of physics. But let's look more specifically in detail, why it is exactly that quantum entanglement does not allow communication. Randomness of measurement: when you measure an entangled particle, the result is random. For example, if you're measuring the spin of an electron, it could be either up or down. You can't control what the result will be, it's entirely random. Because of this, you can't send a specific message using the entangled particles. No control over outcome: since the result of measuring an entangled particle is random, you can't use it to encode a message. You might think that by choosing when to measure the particle, you could send information, but the act of measuring one particle doesn't influence when the other particle will be measured or what the result will be. The only thing that is certain is that the two results will be correlated. Classical communication needed: to compare the results of measurements from the two entangled particles, you need to communicate classically, which means using regular methods like phone calls, emails, or even snail mail. These methods are limited by the speed of light, so you can't send information faster than light using quantum entanglement. No transmission of information: when you measure one particle, you learn something about the other, but this doesn't mean you've sent any information to the other particle. It's more like both particles share a secret that only gets revealed when one of them is measured. No information is transmitted during the measurement, it's just that the outcome of one particle's measurement tells you what the outcome of the other will be if it is measured. In summary, quantum entanglement doesn't allow for communication because the measurement outcomes are random and uncontrollable, and any comparison of results requires classical communication, which is bound by the speed of light. So, while entanglement is a fascinating and mysterious connection between particles, it can't be used to send messages instantaneously. Misconception 2: the double-slit experiment defies logic. The double-slit experiment is often misunderstood as defying logic due to its mind-boggling results. In reality, this experiment is a cornerstone in understanding the wave-particle duality of quantum mechanics. In the experiment, particles such as electrons or photons are fired through two slits onto a screen, creating an interference pattern that suggests wave-like behavior. Interference patterns arise when waves interact with each other, leading to regions of constructive and destructive interference. In the double-slit experiment, particles exhibit wave-like behavior, creating interference patterns on the screen. This phenomenon is not contradictory but rather showcases the dual nature of particles as both waves and particles. To grasp this concept, imagine throwing a pebble into a pond and observing the ripples intersecting and creating patterns. Similarly, in the double-slit experiment, particles behave like waves, interfering with each other to produce distinct patterns on the screen. This experiment highlights the intricate nature of quantum mechanics and challenges our classical understanding of particles. This means that particles, which we usually think of as tiny, solid objects, also behave like waves. When electrons pass through the slits, they interfere with each other in the same way light waves do, creating the pattern of stripes. When scientists first saw this, they were puzzled because it didn't match the way they thought particles should behave. But after much study, they realized that on a very small scale, particles don't follow the same rules as larger objects. Instead, they follow the rules of quantum mechanics, which describe how particles behave like both waves and particles. The double-slit experiment doesn't defy logic, it just shows that the world at a tiny scale follows different rules than we are used to. It helps scientists understand the dual nature of particles and waves, which is a fundamental part of quantum mechanics. Misconception 3: superposition means objects exist in multiple places simultaneously. A common misconception about superposition in quantum physics is that it implies objects can exist in multiple places simultaneously. In reality, superposition refers to the state where a quantum system exists in a combination of multiple states at the same time, each with a certain probability of being observed. Superposition is a fundamental concept in quantum mechanics, allowing particles to be in multiple states until measured, at which point the system collapses into a single state. An iconic example of superposition is Schrödinger's cat, where a cat inside a box is considered both alive and dead until the box is opened and the cat's state is observed. It's important to note that superposition applies at the quantum level and does not have macroscopic effects in everyday life. The probabilistic nature of superposition means that particles can occupy multiple states simultaneously, but upon measurement, they collapse into a definite state. Imagine you have a coin that you flip. When it's in the air, it's not heads or tails yet, it's in between, and you can't say for sure what it is until it lands. Superposition is a bit like this, but for particles like electrons. In the world of quantum mechanics, particles like electrons can be in a state called superposition. This means that they are not in one definite state, like heads or tails, but instead, they have the potential to be in multiple states at once. For example, an electron can be in a state where it has the potential to be in two places at once or spinning in two different directions at the same time. This doesn't mean that the electron is actually in two places or spinning in two directions at once in a way we can see. Instead, it means that until we measure it, we can't say for sure which state it is in. When we do measure it, the superposition collapses into one of the possible states. To make it simpler, think of it like this: if you have a light switch that can be either on or off, in the quantum world, it can be in a superposition of being both on and off at the same time until you actually look at it. Once you look, it snaps into either the on or off position. Superposition isn't about something being in two states at once in a way that defies common sense. Instead, it's about the idea that particles have the potential to be in multiple states and we don't know which one they are in until we measure them. This is a fundamental part of quantum mechanics and helps scientists understand how particles behave at very small scales. Misconception 4: quantum tunneling violates energy conservation. There is a misconception that quantum tunneling violates energy conservation principles, but in reality, quantum tunneling is a phenomenon that aligns with the laws of physics. Quantum tunneling occurs when particles pass through energy barriers that would be classically impossible to overcome. In quantum tunneling, particles exhibit wave-like behavior, allowing them to penetrate energy barriers by exploiting the inherent uncertainty in their position and momentum. This phenomenon is a result of the wave function of particles extending beyond the classical boundaries, enabling them to tunnel through barriers. Uncertainty plays a crucial role in quantum tunneling, as particles' positions and energies are not precisely defined, allowing them to tunnel through barriers with a certain probability. Quantum tunneling has practical applications in various fields, such as electronics, tunnel diodes, nuclear fusion, and scanning tunneling microscopy. These applications demonstrate the real-world significance of quantum tunneling and its consistency with energy conservation principles. Imagine you have a ball that you want to roll over a hill. If the ball doesn't have enough energy, it won't be able to get over the hill and will roll back down. In the classical world, the world of everyday objects, this is always true. However, in the quantum world, things work a bit differently. Particles like electrons don't behave exactly like balls. Instead, they follow the rules of quantum mechanics, which are different from the rules we see in our everyday life. One of these rules is that particles can sometimes tunnel through barriers, even if they don't seem to have enough energy to get over them. This is called quantum tunneling. Here's a way to think about it. Particles are described by something called a wave function, which tells us the probability of finding the particle in a particular place. When a particle encounters a barrier that it doesn't have enough energy to cross, the wave function doesn't just stop. Instead, it decreases, but it continues to exist on the other side of the barrier. This means there is a small probability that the particle can be found on the other side of the barrier, as if it has tunneled through it. Quantum tunneling might seem to contradict energy conservation, but it doesn't. Energy conservation means that the total energy in a closed system remains constant. When a particle tunnels through a barrier, the total energy of the system, including the particle and the barrier, remains the same. The particle doesn't gain or lose energy in the process of tunneling, it simply moves from one side of the barrier to the other. Think of it this way: if you have a ball in a box with a very thin wall, there's a chance the ball could pass through the wall without breaking it, just because of how the rules of the quantum world work. The ball's energy doesn't change when it moves to the other side of the wall, it just takes a different path than we would expect in the classical world. In summary, quantum tunneling is a unique feature of the quantum world that allows particles to pass through barriers without violating the principle of energy conservation. The total energy of the system remains constant, and the particle doesn't gain or lose energy in the process. This helps scientists understand the behavior of particles on very small scales. Misconception 5: Quantum mechanics implies determinism. One common misconception about quantum mechanics is that it implies determinism, where the future state of a system can be precisely predicted given its current state. In contrast to classical determinism, quantum mechanics introduces a level of uncertainty and probabilistic outcomes that challenge the notion of predictability. Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics that states the impossibility of simultaneously knowing both the position and momentum of a particle with absolute precision. This principle highlights the inherent uncertainty at the quantum level and the limitations of predictability in quantum systems. The double-slit experiment is a classic example that illustrates the probabilistic nature of quantum mechanics. When particles are fired through two slits onto a screen, they exhibit interference patterns that cannot be precisely predicted, emphasizing the probabilistic outcomes inherent in quantum phenomena. Quantum mechanics, with its probabilistic nature, introduces a new paradigm that differs from classical determinism and underscores the complexity of the quantum world. In everyday life, things often happen in predictable ways. For example, if you throw a ball, you can predict where it will go based on its speed and the direction you throw it. This idea, that everything happens in a predictable and definite way, is called determinism. However, in the world of quantum mechanics, where tiny particles like electrons and photons live, things work differently. Quantum mechanics describes how these particles behave, and it doesn't follow the same rules as larger objects we see in everyday life. One key aspect of quantum mechanics is uncertainty. This means that on a very small scale, we can't predict with certainty exactly where a particle will be or what it will do. For example, if you try to measure the position of an electron, quantum mechanics tells us that we can only know its position within a range of possibilities. This uncertainty is built into the very fabric of how particles behave at the quantum level. So, quantum mechanics doesn't imply determinism because it allows for uncertainty and superposition. It suggests that particles behave in ways that are not always predictable or deterministic like larger objects. Instead, their behavior is governed by probabilities and the rules of quantum mechanics. This doesn't mean that quantum mechanics is random or chaotic. Scientists use mathematical equations and models to describe and predict the behavior of particles at the quantum level. These predictions are very accurate, but they are about probabilities rather than certainties. In summary, quantum mechanics challenges the idea of determinism by showing that particles can behave in ways that are uncertain and probabilistic. This is a fundamental aspect of how the universe works on a very small scale, and it's why quantum mechanics is such an important and fascinating field of study in physics. Misconception 6: Quantum teleportation involves physical movement. The misconception that quantum teleportation involves physical movement is a common misunderstanding of this intriguing phenomenon. Quantum teleportation is a process in quantum information theory where the state of a quantum system is transferred from one location to another without the physical displacement of the system itself. In quantum teleportation, the quantum state of a particle is encoded and transmitted to a distant location using entanglement and classical communication. This process allows for the transfer of quantum information without the actual movement of particles, challenging our traditional notions of transportation. Entanglement plays a crucial role in quantum teleportation protocols by establishing a strong correlation between particles that enables the instantaneous transfer of quantum states. Through the utilization of entanglement and quantum superposition, quantum teleportation showcases the remarkable potential of quantum information processing and communication. By clarifying the mechanism behind quantum teleportation, we can appreciate the innovative applications of quantum technology in the modern world. Imagine you have two particles that are entangled. Let's call them particle A and particle B. Particle A is the particle you want to teleport, and particle B is the particle where you want to teleport the information about particle A. To teleport particle A's properties to particle B, scientists perform a measurement on particle A. This measurement reveals information about its quantum state without physically moving particle A itself. However, the act of measuring particle A changes its state. Because particle A and particle B are entangled, the change in particle A's state is instantly mirrored in particle B. This means that the information about particle A's misconception 7, quantum computing solves all computational problems instantly. It is a common misconception that quantum computing is a magical solution that can instantly solve all computational problems. While quantum computing offers significant advantages over classical computing in certain areas, it is not a panacea for all computational challenges. Quantum computing harnesses the principles of quantum mechanics to perform computations using quantum bits or qubits, which can exist in superposition and entanglement states. This allows quantum computers to process vast amounts of information simultaneously and potentially outperform classical computers in specific tasks such as factorization and optimization. However, quantum computing also has limitations, including the susceptibility to errors due to decoherence and the need for error correction mechanisms. Quantum algorithms, such as Shor's algorithm for integer factorization and Grover's algorithm for unstructured search, demonstrate the power of quantum computing in solving certain problems efficiently. While quantum computing shows promise in revolutionizing various fields, it is essential to recognize its capabilities and limitations to effectively harness its potential for solving complex computational challenges. Quantum computing is a cutting-edge field that offers new ways to tackle complex problems, but it doesn't mean it can solve all computational problems instantly. Here's why. Firstly, quantum computers excel at specific tasks like factoring large numbers quickly or simulating molecular structures, which are difficult for traditional computers. However, they aren't universally better for all tasks. For everyday uses like browsing the web or basic calculations, regular computers remain highly effective. Secondly, programming quantum computers is very different from programming traditional computers. Developers need to write algorithms specifically for quantum hardware, which requires specialized skills and knowledge. Thirdly, quantum systems are sensitive to errors caused by noise and disturbances. Developing error correction methods is crucial but adds complexity to quantum computing. Moreover, quantum computers are still in early stages. Current models have limited qubits, the units of quantum information, and are prone to errors. Building more powerful and reliable quantum computers is an ongoing challenge. In conclusion, while quantum computing shows promise for solving certain complex problems faster than traditional computers, it's not a solution for all computational challenges. Understanding its strengths and limitations is key to harnessing its potential effectively in the future. Misconception 8: Quantum gravity will unify all forces. The misconception that quantum gravity will unify all forces and serve as the ultimate theory of everything overlooks the complex challenges in reconciling quantum mechanics with general relativity. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity explains the force of gravity on a cosmic scale. Combining these two theories into a unified framework, known as quantum gravity, has been a long-standing goal in theoretical physics. The search for a quantum theory of gravity faces significant obstacles, including the inherent mathematical and conceptual differences between quantum mechanics and general relativity. Sabine Hossenfelder, a prominent physicist, emphasizes the need to critically assess the assumptions and approaches in quantum gravity research to avoid unfounded claims of a unified theory. While quantum gravity holds profound implications for understanding the fundamental nature of the universe, it is essential to acknowledge the complexities and uncertainties inherent in this quest for a unified theory of physics. Quantum gravity is a concept in physics that aims to merge two major theories: Einstein's general relativity and quantum mechanics. These theories describe very different aspects of the universe. General relativity explains gravity as the curvature of spacetime caused by mass and energy. It works well for understanding large-scale phenomena like planetary orbits and the behavior of galaxies. On the other hand, quantum mechanics deals with the behavior of particles at the smallest scales. It describes how particles like electrons and photons behave in terms of probabilities and wave functions. The challenge with quantum gravity lies in reconciling these two theories. General relativity uses smooth, continuous mathematics to describe spacetime, while quantum mechanics relies on probabilistic calculations and discrete energy levels for particles. Combining these frameworks into a single theory that accurately describes both gravity and quantum phenomena has proven difficult. Furthermore, while both general relativity and quantum mechanics have been extensively tested and confirmed in their respective domains, experimental evidence for theories of quantum gravity is still lacking. This means that scientists cannot yet directly verify which theoretical approach accurately describes gravity at the quantum level. Researchers are exploring alternative theories, such as string theory and loop quantum gravity, which propose different ways of approaching the unification of gravity with the other fundamental forces. These theories offer new mathematical frameworks and physical concepts but also face significant theoretical and experimental challenges. In conclusion, quantum gravity represents a major frontier in physics, aiming to deepen our understanding of how the universe works at both the largest and smallest scales. However, achieving a complete and experimentally validated theory of quantum gravity remains one of the most complex and elusive goals in modern physics. Misconception 9: Quantum decoherence destroys superpositions. Quantum decoherence is a natural process that happens when a quantum system interacts with its environment. In simpler terms, it means that when a tiny particle, like an electron, interacts with things around it, like other particles or even light, it loses its special quantum properties, like being in multiple states at once. Now, superposition is one of those special quantum properties. It means that a particle can exist in many different states simultaneously, like being both here and there at the same time. This idea might sound strange, but it's a fundamental part of how the tiniest particles in the universe behave according to quantum mechanics. Here's where decoherence comes in. When a particle in superposition interacts with its surroundings, such as bouncing off other particles or being hit by light, these interactions cause the delicate quantum state to become entangled with the environment. This process of entanglement means that we lose the ability to see the superposition directly because the particle's state becomes intertwined with the state of its environment. However, it's important to note that decoherence doesn't destroy superpositions altogether. Instead, it makes them harder to observe or detect. The quantum state of the particle and its entangled environment still technically exists, it's just that we can no longer isolate and observe the pure superposition state by itself. Scientists study and try to control decoherence because it affects how we can use quantum systems in technologies like quantum computers. By understanding how decoherence works, researchers can develop ways to protect and preserve quantum states for longer periods, allowing us to harness the full potential of quantum mechanics in future technologies. In summary, while decoherence makes superpositions harder to detect or maintain in certain situations, it doesn't completely erase the fundamental quantum properties of particles. It's a natural part of how quantum systems interact with their surroundings, and studying it helps us better understand and utilize the strange and fascinating world of quantum mechanics. A common misconception is that quantum decoherence destroys superpositions, leading to the collapse of quantum states into classical behavior. In reality, quantum decoherence is a natural process that plays a crucial role in the transition from quantum to classical behavior in macroscopic systems. Quantum decoherence occurs when a quantum system interacts with its environment, causing the system's quantum superposition to lose coherence and exhibit classical-like behavior. While decoherence may appear to destroy superpositions, it actually leads to the emergence of classical features in macroscopic systems by suppressing quantum interference effects. Controlling decoherence poses both challenges and benefits in quantum systems. While decoherence can limit the coherence time of quantum states, leading to errors in quantum computations, it also enables the stability and robustness of classical behavior in everyday objects. Understanding and managing decoherence is essential for harnessing the power of quantum technologies and advancing quantum information processing capabilities. Misconception 10: Quantum weirdness means quantum physics is incomprehensible. The notion that quantum physics is incomprehensible due to its weird nature is a misconception that overlooks the logical consistency and beauty of quantum phenomena. While quantum mechanics indeed presents counterintuitive aspects, such as superposition and entanglement, these features are not inherently illogical but rather reflect the intricate nature of the quantum world. Embracing the mystery and beauty of quantum physics can lead to a deeper appreciation of the underlying principles that govern the behavior of particles at the smallest scales. Despite its complexities, quantum theory has been remarkably successful in explaining a wide range of phenomena, from atomic structure to quantum computing and cryptography. By exploring the applications of quantum theory in various fields and marveling at the elegance of quantum phenomena, viewers can gain a newfound perspective on the captivating world of quantum physics. Rather than viewing quantum weirdness as a barrier to understanding, it can be seen as an invitation to explore the fascinating and enigmatic realm of quantum mechanics. Some people find quantum physics confusing because it describes a world that behaves very differently from what we experience in our daily lives. Quantum physics deals with how tiny particles like electrons and photons behave at the smallest scales imaginable. However, thinking that quantum physics is incomprehensible is not accurate for several reasons. Firstly, quantum physics has proven itself incredibly accurate in predicting and explaining the behavior of particles in experiments. Scientists have developed mathematical theories that reliably describe what happens in the quantum world. Despite the strange behavior of quantum particles, these theories consistently match experimental results. Secondly, quantum physics is supported by a wealth of experimental evidence. Over many decades, scientists have conducted numerous experiments confirming the principles of quantum mechanics. These experiments demonstrate phenomena like superposition, particles existing in multiple states at once, wave-particle duality, particles behaving as both waves and particles, and quantum entanglement, particles being interconnected in ways that defy classical understanding. Thirdly, quantum mechanics isn't just theoretical, it has practical applications. Technologies like semiconductors, essential for computers and smartphones, rely on quantum principles. Emerging technologies such as quantum computing and quantum cryptography are also grounded in quantum mechanics and hold promise for transforming fields like computing and data security. Lastly, while quantum physics challenges our intuition about the world, it's not incomprehensible. Scientists have developed conceptual frameworks and mathematical tools to understand and work with quantum phenomena. These frameworks enable researchers to make sense of quantum behaviors and apply them in technology and fundamental scientific exploration. In this video, we have debunked several key misconceptions about quantum physics, shedding light on the true nature of this fascinating field. From clarifying misunderstandings about quantum entanglement and superposition to addressing misconceptions surrounding quantum tunneling and decoherence, we have explored the intricate and often counterintuitive aspects of quantum phenomena. It is essential to approach scientific concepts with a critical mindset, questioning assumptions and seeking a deeper understanding of the underlying principles. By embracing the complexities of quantum physics and engaging with the mysteries it presents, viewers can expand their knowledge and appreciation for the wonders of the quantum world. We encourage you to delve further into the realm of quantum physics through additional resources and continue exploring the captivating realm of quantum mechanics. Join the conversation by sharing your thoughts and questions on quantum phenomena, and don't forget to engage with our channel for more insightful content. Thank you for watching Mysterious Nuggets.